Hello everyone, I'm Yinhao from University of Science and Technology of China. Today I'm going to present our recent work on learning-augmented streaming algorithms for approximating max cut. This is a joint work with Peng from USTC and Ali Vakilian from TTIC. So in the max cut problem, we are given an undirected, unweighted graph G. The goal is to find a bipartition of the vertex at V into S and T, such that the cut value, the number of edges with one endpoint in S and the other in T, is maximized. This problem is NP hard, so people focus on designing approximation algorithms. We say an algorithm for max cut achieves an alpha approximation if it outputs a cut such that the cut value is at least alpha times OPT and at most OPT. Here, OPT refers to the cut value of some fixed optimal solution. There is a simple greedy algorithm that achieves a half approximation. Similarly, a local search algorithm can also achieve the same approximation ratio. The best known approximation ratio is 0.878 by Gomez and Williamson based on SDP rounding. This is also the best possible under the unique games conjecture. In the big data era, as the volume of data grows rapidly, people are more focusing on designing algorithms in the streaming model. In this model, the input graph is presented as a sequence of edge insertions and deletions. Let me give you an example. Here are the vertices, and the edges arrive one by one in a sequence. When the algorithm receives an edge, it can perform some operations, such as storing the edge or updating certain counters. This is an edge deletion. The goal of the algorithm is to scan the stream in one pass and find the solution at the end of the stream while using as small space as possible. If the graph stream contains only edge insertions, we call it an insertion-only stream. If it contains both edge insertions and deletions, we call it a dynamic stream. In this work, we focus on estimating the value of max cut in the streaming model. In this setting, the algorithm only needs to output a value instead of a cut. There is a trivial half approximation algorithm using only O log n bits of space. It simply counts the number of edges m during the stream and outputs m over 2. There has been a line of works exploring the trade-offs between approximation ratio and space for this problem. Hapralov and Quatron's work culminated in showing that any randomized algorithm that achieves half plus epsilon approximation requires omega n bits of space. We aim to surpass this barrier under the framework of learning-augmented algorithms, also known as algorithms with predictions. These algorithms use machine learning or data mining techniques in classical algorithms to improve their performance beyond worst-case guarantees. In this framework, the algorithm has oracle access to a predictor, which typically provides some information about the optimal solution. The goals are twofold. First, if the predictions are highly accurate, the algorithm should significantly outperform the best-known classical algorithm without predictions. Second, even if the prediction quality is low, for example, the prediction may be corrupted by an adversary, the algorithm should still perform no worse than the best-known classical algorithm. One more thing, this is an exciting and rapidly growing research area, full of opportunities. If you are interested, there is a great webpage with an up-to-date repository of publications in this field. In this work, we consider the following prediction model called epsilon accurate predictions. Let X star denote some fixed but unknown optimal solution. It's an n-dimensional vector where each entry is either -1 or +1, representing the part of its corresponding vertex. Our algorithm has oracle access to a prediction vector Y, where each entry YV is correct with probability half plus epsilon. Specifically, for each vertex V, the probability that YV equals X star V is half plus epsilon. And these predictions are independent. As you can see, this prediction model is only slightly better than random guesses. By the way, variants of this prediction model have also been used to design improved approximation algorithms for max-cut and other constraint satisfaction problems. So what kind of results can we achieve with this prediction model? We have the following results. Given oracle access to an epsilon accurate predictor, there is a single pass streaming algorithm that achieves a half plus omega epsilon square approximation for estimating the max cut value with probability at least 2/3. The algorithm uses poly 1 over epsilon words of space in insertion-only streams and poly 1 over epsilon log n words of space in dynamic streams. Here are some remarks. First, by leveraging predictions, we bypass the classical half plus epsilon approximation and omega n space trade-off established by Kapralov and Kratron. Second, our algorithm can actually work in a weaker streaming model. Specifically, we can assume that the predicted label of each vertex is associated with its edges as they appear in the stream. In this model, no additional space is required to store the predictions. Now let's move on to our algorithms. We will start with a simple case where the input graph is a low-degree graph. Specifically, the maximum degree delta is less than epsilon squared times the number of edges. The algorithm is quite simple. We maintain a counter X initialized to 0. When an edge UV arrives in the stream, we query the oracle or predictor for the predicted labels YU and YV of the endpoints U and V. If YU does not equal YV, then we increment the counter X. At the end of the stream, the algorithm outputs the value of X. As you can see, this algorithm just directly follows the predictions, and we can show that this simple strategy already achieves a better than half approximation. Specifically, given oracle access to an epsilon accurate predictor, this algorithm provides a half plus epsilon square approximation with probability at least 2/3 for low-degree graphs. The space complexity is only 01 words, since X is at most the number of edges. Next, let's consider how to generalize the previous algorithm to handle general graphs. A natural idea is to first divide the vertex set V into high-degree vertices and low-degree vertices, and then handle them separately. To distinguish between them, we set the threshold to be epsilon squared times the number of edges. A vertex is considered high degree if its degree is at least epsilon squared m, otherwise it's low degree. For simplicity, I will first describe the offline algorithm and then discuss how to implement it in the streaming model. The algorithm is as follows. We first divide V into high-degree vertices H and low-degree vertices L. Then we consider two candidate cuts. The first cut is constructed by applying the previous low-degree algorithm to GL, the induced subgraph of L, and then extending this cut to the entire graph by handling the vertices in H greedily. Let me show you a concrete example. So in this graph, we have already divided all the vertices into high degree vertices H in red and low degree vertices L in blue. We first run the low degree algorithm on GL. What does the low degree algorithm do? It simply follows the predictions. So we obtain L plus, L minus, where L plus is the set of vertices in L with predicted labels +1, and L minus is the set of vertices in L with predicted labels -1. Then we perform a greedy extension of L plus, L minus using vertices in H. For each vertex in H, for example, consider this yellow vertex V in H. We check the number of edges between V and L plus, as well as the number of edges between V and L minus. Then we place V in the side with fewer edges. For example, we place V in L plus in this case, because our goal is to maximize the cut value. We repeat this process until all vertices in H are assigned. And then we obtain the final cut. You can verify that the value of this candidate cut is at least this value. The first term is the number of edges between L plus and L minus. Additionally, since we perform a greedy extension using vertices in H, each vertex V in H contributes at least the maximum of EVL plus and EVL minus to the cut value. Another cut we consider is simply HL, like this, and the cut value is EHL. Finally, we return the larger cut value of the two candidates. And we can show that given Oracle access to an epsilon accurate predictor, this offline algorithm achieves a half plus omega epsilon square approximation for general graphs with probability at least 2/3. In the rest of the talk, I will discuss how to implement the offline algorithm in different streaming settings. The main challenge here is that we don't know H and L in advance, and we have to detect them during the stream. Let's first consider random order streams. In this model, the edges of the input graph are presented in a uniformly random order. Basically, we'd like to simulate the offline algorithm in this model. The algorithm is as follows. During the stream, we store the first poly 1/epsilon edges. For example, the red edges here are the first poly 1/epsilon edges in the stream. Then we use these edges to identify a vertex set H tilde. Specifically, H tilde consists of the endpoints of the first poly 1/epsilon edges. And we can show that H tilde contains all the high degree vertices with probability at least 2/3. Intuitively, high degree vertices are connected to many edges in the graph. As a result, they are highly likely to appear in the first poly 1/epsilon edges in the random order stream. During the remaining edges of the stream, for each vertex V in H tilde, we maintain the number of edges between V and L tilde plus, as well as the number of edges between V and L tilde minus. Here, L tilde plus is the set of vertices in L tilde with predicted labels +1, and L tilde minus is the set of vertices in L tilde with predicted labels -1. We also maintain the number of edges between L tilde plus and L tilde minus. Okay, this is the streaming phase. Now we have stored some edges and maintained several counters. At the end of the stream, we can exactly detect H from H tilde, since H tilde contains all the high-degree vertices with probability at least 2/3. We can use the stored information to compute the degrees of the vertices in H tilde and compare these degrees against the threshold to determine which vertices belong to H. So the red vertices correspond to H and the blue vertices correspond to L. Now we can exactly compute the values of two candidate cuts, ALG1 and ALG2, using the stored edges and counters. Finally, we output the maximum of ALG1 and ALG2. The analysis follows directly from the offline algorithm. We can show that given oracle access to an epsilon accurate predictor, this algorithm is a half plus omega epsilon square approximation with probability at least 2/3. The space complexity is only poly 1 over epsilon words, since you can easily check that the size of H tilde is at most poly 1 over epsilon. Now let's move on to arbitrary order streams. In this model, the edges of the input graph are presented in arbitrary or adversarial order. The algorithm is as follows. Instead of storing the first poly 1 over epsilon edges in the stream, this time we use reservoir sampling to sample poly 1 over epsilon edges uniformly at random from the stream. But this time we can only obtain H tilde at the end of the stream. As before, we can also show that all the high-degree vertices belong to H tilde with probability at least 2/3. At the same time, we use sketching techniques designed for frequency estimation, such as count-mean sketch, to estimate the number of incident edges related to high-degree vertices. At the end of the stream, we obtain H tilde using the stored edges. But since we can't retrieve H exactly anymore, we can only compute ALG1 and ALG2 approximately, and finally output the maximum of them. We can show that given oracle access to an epsilon accurate predictor, this algorithm in arbitrary order streams also achieves a half plus omega epsilon square approximation with probability at least 2/3. And the space complexity is also poly 1 over epsilon words. Finally, let's consider dynamic streams. Recall that the dynamic stream contains both edge insertions and deletions. In this setting, we use L0 sampling to sample poly 1 over epsilon edges from the dynamic stream. Specifically, we maintain poly 1 over epsilon L0 samplers. Each L0 sampler can sample one edge uniformly at random from the dynamic stream. We can show that these L0 samplers provide poly 1 over epsilon different random edges from the dynamic stream. And to estimate the number of edges incident to vertices in H, we can also use count-mean sketch in the dynamic stream. We can show that given oracle access to an epsilon accurate predictor, this algorithm also achieves a half plus omega epsilon square approximation with probability at least 2/3. The space complexity in this case is poly 1 over epsilon log n words, since each L0 sampler requires poly log n words of space. To conclude, in this work, we give the first learning-augmented streaming algorithm for estimating the max cut value of a graph. Specifically, by leveraging epsilon accurate predictions, we provide a single-pass streaming algorithm that achieves a half plus omega epsilon square approximation with probability at least 2/3. Our algorithm uses poly 1 over epsilon words of space in insertion-only streams and poly 1 over epsilon log n words of space in dynamic streams. This result contrasts with the lower bound in the classical streaming setting without predictions. Our work also leaves some open problems. First, in this work, we only consider unweighted graphs, and it would be interesting to extend our results to weighted graphs. Another open question is to establish lower bounds on the trade-offs between approximation ratio and space complexity for learning-augmented streaming algorithms. Okay, this is the end of my talk. Please refer to our paper for more details. Thank you for your attention.